Okay, well, welcome to our eighth learning workshop. We're going to be going over the gas laws, and fortunately, the gas laws are actually um, it's a fairly easy to use the gas laws. They're pretty straightforward once you know them. It's just about knowing them and then knowing how to apply them. So let's go ahead and take a look at the gas laws. Before we jump into the actual laws themselves, we want to take a moment to describe the kinetic molecular theory of gases. And the kinetic molecular theory of gases is essentially the main ideas behind what makes up an ideal gas. This basically describes the behavior of gases under more or less normal or ideal conditions. So it basically says that gases have a large number of very small particles that are in constant random straight line motion. So they're moving in straight lines and they're constantly bouncing off each other. Secondly, the combined volume of all particles of a gas is negligible relative to the total volume of a container. So what does that mean? That means that, let's say if you have a container of gas, let's say you have a huge 50-gallon drum. Okay, imagine this is a giant 50-gallon drum, and it's completely filled with gas, completely filled with air. Then if you were to condense all of that gas into one tiny part, if you were to condense all of that gas into the smallest volume possible, you would see that maybe all that gas fits into this tiny little spot on the bottom, that little black spot on the bottom left corner. So the combined volume of all the gas particles is negligible compared to the total volume of the container. Um, Next, that the attractive or repulsive forces between gas particles are negligible. So with number three, kind of think of it like this. Let's say, for example, you had a very powerful magnet and you put it close to a piece of metal. You would feel the pull and the magnet might even jump out of your hand and attach to it, right?
Right.
What if you had, shall we say, that same powerful magnet, but let's say you strapped it to a wall and you fired a metal bullet that would respond to the magnet. We fired a metal bullet from a gun and fired it right past that magnet. Would that magnet alter the course of that bullet at all, do you think? What do you think? Yeah, and as Ethan said, well, yes, but not much. And the truth is, it would alter it practically almost not at all. And the reason is because the the bullet is in the presence. The bullet is in the presence of that magnetic pull over such a tiny period of time that it barely has time to affect the motion of the bullet at all. And that's basically what happens to these gas particles. They do have a sort of attraction that's similar to a magnetic attraction, although it's more of an electrostatic type attraction between if polar molecules, it's a permanent dipole, but between non-polar molecules, you'll learn more about the types of intermolecular forces later, but it all has to do with partial positives and partial negatives on the molecule itself. But yeah, so these attractive forces are um, they're not enough, even in cases where it's like water, where water has really really strong attractive forces. because they're moving so fast in the gas phase, they're not really able to impact each other very much. And so it's essentially as if those attractive and repulsive forces did not really exist. And then number 4 says energy can be transferred between molecules during collisions, but as long as the temperature remains constant, the average kinetic energy of the particles remains the same. So in other words, the collisions are elastic. There's no loss of energy between the collisions. No, in truth, there's no such thing as a perfectly elastic collision. So I mean, but for the most part, it's about as close to an elastic collision as you can get when the gas particles collide. Um, so that the key thing here is that number 4, and then number 5 basically says the average kinetic energy of the particles is proportional to the absolute temperature. So that's what temperature is a measure of. And that's the biggest difference between temperature and heat. Heat is the total measure of thermal energy, whereas temperature is a measure of the average kinetic energy of the particles. This is why some things take a very long time to cool down, such as a pool of water, and some things take a very short time to cool down, such as air. Um, it's very easy to cool down air because there's very few particles in air compared to the number of particles in water. Plus, the particles in water can hold more heat, or have more heat. They hold more heat per degree Celsius than, say, other types of particles. So the ability to hold heat, as you might have gotten from the thermochemistry unit, thermochemistry workshop that we did, and although I don't know if we got quite to that, but the ability to hold heat is called specific heat capacity. That's the ability of a substance to hold heat per unit of temperature. Metals have a very low specific heat. Gases have a very low specific heat. Uh, Water has a very high specific heat because of its very strong attractive forces. But in all those cases, the average kinetic energy of the particles is still proportional to the absolute temperature. At the same temperature, the particles of all gases have the same average kinetic energy. That is important. It doesn't matter what the gas is, the particles of all gases have the same average kinetic energy at the same temperature. So this makes it possible to describe, in an idealized form, these tenets describe your typical ideal gas. Okay. So these are physical characteristics of gases that we're going to be relating in the following gas laws: volume, pressure, temperature, and number of atoms or molecules. And we'll typically use units of liters, pressure in ATM, Kelvin, and moles. We always use absolute temperature when it comes to molar mass. We always use absolute temperature, we always use absolute temperature when it comes to the gas laws, because only the absolute temperature scale can allow us to compare the uh, with the other features. And you'll see more about that when we actually get into the gas laws themselves. So let's look at the first gas law, Boyle's law. We have a picture of Robert Boyle here, sometimes referred to as the father of modern chemistry. Um, Boyle's law basically states that pressure and volume are inversely related at constant temperature. So in other words, as one goes up, the other goes down. This pressure times volume is equal to K. You might be like, well, that doesn't look like an inverse relationship to me. But if you were to rewrite this equation, you could say, well, pressure is equal to some constant K times 1 over volume. You're like, oh yeah, that looks like an inverse relationship to me. So pressure and volume are inversely related. And if you think about this, like if you think about like you're packing a suitcase, okay? You're packing a suitcase and you want to pack a bunch of stuff in, and well, there's not enough room in the suitcase because you've packed a little bit too much. If you want to get that suitcase closed, you have to apply a lot of pressure and push it down really hard, because if you apply a lot of pressure, you'll squeeze it into a smaller volume and then you can close the suitcase. It sometimes works better than others. So this is an example of Boyle's law in action. You have a piston that holds 1 liter of gas, 1 atm. If you double the pressure to 2 atm, the volume will be cut in half. As an inverse relationship. Cool. And then we have Monsieur Jacques Alexander Charles, physicist and inventor, came up with Charles' law. And with the advent of this law, we got, it says volume of a gas varies directly with the absolute temperature and constant pressure. In fact, it was through these experiments that you discover what the absolute temperature actually is. Because it wasn't really known that there was a minimum temperature. But as temperature increases, so does volume. As you can see, you double the temperature from 200 to 400 Kelvin, and the volume will double from half a liter to a full liter, as long as the pressure remains the same. And then you can see that by graphing the volume at different temperatures, they were able to determine, even though they couldn't get below a certain temperature at that time because of technology, they just didn't have the technology to make it as cold, colder than right about here. You can extrapolate that straight line relationship, and they kept on coming up with the same minimum temperature here of about negative 273 Kelvin, or negative 273 degrees Celsius, and they decided to make a new temperature scale based on that, with this as the absolute lowest temperature possible. Because obviously you can't get less than 0 volume, right? So next is Avogadro's law, and he's kind of a weird looking dude, I'm not going to lie. Not to make fun of him or anything, but you know. The constant temperature and pressure, the volume of a gas is directly related to the number of moles. So basically, and this is pretty obvious, like if you have more moles of gas, then you're going to have more volume. Volume is directly related to the number of moles. So V1 over N1 is equal to V2 over N2. You're comparing two samples. You change one, you change the other. As long as pressure and temperature are the same, if you double the amount of particles in the cylinder, that's going to double the volume of the container. And forgive me if I'm going too fast through these, but we'll kind of put these all together in just a little bit. And then there's Joseph Louis Gay-Lussac, who's also a scientist in the 1800s. And he discovered that at constant volume, the pressure and absolute temperature are directly related. As temperature increases, so does pressure. This is why they warn you to always be careful about letting certain compressed air containers get too warm or get too hot. Because if you heat up a container of compressed air And I somehow have a sneaky suspicion that Ethan may have done this, but if you like throw a container of compressed air into the fire, like it'll explode, and it can be very dangerous. You have to be really, really careful about that.
You'd be right.
Yeah, but yeah, so and you double the temperature, you double the pressure.
So
Now,
Ethan already experimentally proven the Gauss-Stack law.
yeah, exactly.
Yeah, I should get my name on a paper somewhere.
um, so all those previous four laws can be integrated into one single equation. The P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And basically, the P1 V1 N1 T1, those are initial sets of conditions. And the P2 V2 N2 T2 are final sets of conditions. And the interesting thing about this is that because pressure, volume, number of moles, and temperature describes all of the most essential components, quantitative components of a gas, this effectively ends up giving you this ideal gas law constant R. And so it's true for any gas that P1 V1 over N1 T1 is always going to give you the same R value. But the cool thing about this equation is that if, let's say for example, you don't have pressure. Let's say like you don't need pressure because pressure's not changing, okay? Well, if pressure's not changing, you can ignore it. And it's just V1 over N1 T1 is equal to V2 over N2 T2. And then if you, let's say you have N1, the number of moles is constant and everything else is changing, well then it's P1 V1 over T1 is equal to P2 V2 over T2. And likewise, anytime you have something that is changing, you can eliminate, let's say moles and temperature are constant, they're not changing. So you get rid of both of those, and it's just Boyle's law. P1 V1 is equal to P2 V2. So all of the gas laws are contained in this one single equation. It's really nice because you can kind of be lazy and not have to worry about memorizing things too much if you know this one combined gas law. Now let's do some practice problems. What do you say? What do you say? So it says if you expand 10.2 liters of a gas to 2.05 times 10 to the fifth milliliters, and the temperature is raised from 24.5 degrees Celsius to 98.0 degrees Celsius, what would the new pressure be if the original pressure was millimeters of mercury? So with a problem like this, one of the things that I might recommend is to go ahead and write that combined gas law and see which things are changing and which things are not. P1 V1 is equal to over N1 T1 is equal to P2 V2 over N2 T2. Now let's see, is pressure changing? What do we have here? Is there any one of these variables that's not changing?
Number of moles.
Number of moles. Yeah, and other than that, everything else is changing, right?
Yes.
So we'll use P1 V1 over T1 is equal to P2 V2 over T2. And one of the things I usually like to do at this point is go ahead and list my variables. P1 V1 T1 is equal to P2 V2 T2. Okay, now it doesn't The truth is, it doesn't really matter which one we decide are ones and which ones we decide are our twos, but P1, V1, and T1 have to describe the same set of conditions, which is why I usually say the P1, V1, and T1 are my initial conditions. So what's my initial pressure?
millimeters of mercury.
You got it, 742 millimeters of mercury. By the way, I'm trying something new with my microphone. Am I coming through okay? Do I sound understandable?
The clarity is superb.
Okay, excellent. All right, now let's look at V1 then. What's the initial volume?
10.2 liters.
Okay, 10.2 liters. Oh, what was that? I don't like that. I'm going to try that again. 10.2 liters. And what's the initial temperature?
24.5.
24.5.
Yeah, 24.5. Very good. Degrees Celsius. And what's the initial pressure?
Isn't that what we're solving for?
That is what we're solving for. Very good. And what's the initial volume? Or what's the final volume, rather?
2.05 times 10
Uh-huh.
to the 5th milliliters.
Very good. 2.05 times 10 to the 5th milliliters. And then what's the final pressure, or temperature, rather?
98 degrees Celsius.
Excellent. All right, so whenever you get these, once you have your variables listed, you can actually see if there's any inconsistencies there. For this equation to work, the P1 V1 over T1 is equal to P2 V2 over T2, you have to have the units match. Also, the temperature must be in what unit?
Kelvin.
Kelvin.
Kelvin. Exactly, it has to be based on the absolute temperature scale, otherwise you won't get the correct answer. So I'll go ahead and add 273 to each one of my Celsius temperatures, and that's going to give me 297.5 Kelvin here. And if I add 273 here.
I have just a quick question regarding temperature, since we're on that right now.
Sure.
Do you ever add the 0.15 when you're adding to get to Kelvin, or do you just add the 273?
It's a good question. You can always add the 0.15. Whether or not it will really make a difference, oftentimes it doesn't, just because with these other ones, you usually don't get more significant figures than, say, 3 or so. So it usually doesn't make a difference if you add the 1.15 or not. But if you want to be a little bit more accurate, you can always add the 0.15. That's totally fine.
Okay.
But for practical purposes, I mean, it's a very good question, but for practical purposes, yeah, it's for these problems, it's not going to make or break it. So for simplicity, we can just use 273.
Yeah, and especially in the context
Okay.
of any test you might be taking, you likely have a multiple choice question. And in that case, the 273 versus 273.15, it's not going to make any difference whatsoever.
Okay.
Yes.
Thank you.
But good question. Good question. All right, now what about the volumes? Are the volumes okay as is, or do we have to do anything?
Excuse me
I have
for
to
one.
do it. Exactly. Because one of them is milliliters, the other is liters. Now, does it matter which one we convert to?
Convert it to liters.
It actually doesn't matter. You could actually convert liters to milliliters, or you can convert milliliters to liters. It really doesn't matter either way, as long as the units are the same. But we'll go ahead and convert milliliters to liters. That's totally fine. So I'll go ahead and put the milliliters on bottom here. I'll convert it to liters. Does anybody remember how many milliliters are in a liter?
1,000.
1,000. So we got 1,000 milliliters in 1 liter. And if I do that, I realize that this is going to actually expand to 2.05 times 10 to the second, which is going to be 205 liters. I expand it from 10.2 liters to 205 liters. And then we can go ahead and do the pressure. Now we can solve for the pressure. Now we have the temperatures. Okay, we're solving for P2. Now, I want to show you a little trick that I find actually very helpful. When doing these gas law things, sometimes I like to go ahead and convert this into the cross-multiplied form. So I could do the cross-multiplied form. I just cross-multiply this equation, and I'm going to get P1 V1 times T2 is equal to P2 V2 times T1. Now here's the thing. Once I have the fraction eliminated, I know I'm solving for P2. So I can just isolate P2 by dividing both sides by V2 and T1. Okay. So V2 and T1 cancel out over here, and I see that P2 is equal to P1 times V1 times T2 divided by V2 and T1. And I could plug the numbers in, or I could just go ahead and use the numbers that I have over here. It's totally fine either way. I'll rewrite the equation and I'll plug in the numbers over on the other side. So it's P1 742.0 millimeters of mercury times V1 10.2.
Good question, and we will get to that. So after Professor Dupont solves this problem, we will grapple with the question that Koti asked, which is why did we not convert why did we not convert the pressure from millimeter mercury to atmosphere? So we'll do it after the problem is solved. Thank you for the question.
And actually, that's an easy one to answer. The truth is, you definitely could convert it to ATM, but since it doesn't ask for the pressure in a specific unit, in this case, you can probably leave it as millimeters of mercury. If it asked for the pressure in ATM specifically, then you would have to convert it to ATM.
And also,
now you'll notice here that if I look at the units, K and liters actually cancel out. And I'm left with a unit of millimeters of mercury. And that makes sense because that's what I want. I should be getting a unit of pressure.
But also, if I may add, the reason we made the choice of not converting the millimeter mercury to atmosphere, which we could have done, is that the conversion from millimeter mercury to atmosphere is the conversion factor. It's a multiplication operation. So in other words, one, half a dozen of the other.
Yeah.
However, had we not converted the temperature to Kelvin, we would have run into a problem because the temperature, it's an addition operation, it's not a factor. The same with volume. Should we have kept the mil instead of going to liter? Sure, we could have done that. But again, we could not do it with temperature because it's not an operation, it's not a multiplication, it's not a conversion factor operation, it's an addition operation. Does that make sense?
Yeah.
All right.
Cool. Oh, by the way, I just wanted to mention this real briefly. I feel I am getting some feedback and echoing. I don't know if anybody's not using a headset, but if you don't have a headset on, that might be useful to use just to kind of eliminate some of that feedback echo. And
Okay,
what do
let
we
me,
get for the?
yes.
And what do we get for that pressure? What do we get for that pressure answer? Multiplying everything on top and divide by everything on bottom. What did we get for that? Multiplying everything on top and
I
dividing everything.
I got
46.5.
45.6.
45.6 sounds about right, yeah.
Oh, I don't know.
Is this a little bit better as far as the noise, the sound quality?
Oh, it's great. So much
Okay.
better.
Okay, thank you.
Now, just as an FYI here, if you did not get that, it's possible what you did was you divided by the 205, but then you multiplied by the 297.5. You have to remember that unless you put, you have to do one of two things here. You either have to divide by each thing in the denominator, or you have to divide by the 205 times 297.5, but you have to put that denominator in parentheses, the whole thing in parentheses. So to give you an idea, like how this would you'd have to show up on your calculator. It would basically be you could do 742 times 10.2 times 371 divided by the 205, and then divide by again 297.5.
Oh,
You have to
okay.
hit divide by for both of those. If you don't, it will end up giving you the wrong answer. Alternatively, if you wanted to do the multiplication sign instead of a divide sign for that, you have to put a parentheses around it. Divide by
Oh, so
205
that's what
times
I did.
297.5.
I
So
put
you
the
have to do one
first
of those
phrase.
two things, otherwise you'll get it wrong.
I put the first phrase in parentheses and then divided by the second part in parentheses.
You can do that, that's fine. But honestly, I will encourage you to, I said the easiest thing to do here really is this. Don't
Divide
use
by.
parentheses at all, just multiply by everything on the top and literally divide by every single thing on bottom. And that will
Yes.
do it, it'll get you the answer to the problem the quickest, and it will lessen the opportunities that you have to make mistakes.
Noted. Okay.
Yes.
All right.
Just real quick. Anna, did you get 46.0?
Yeah,
Okay, that's what I got because I
that's
went
what I
back
got
and
too.
just made sure that I did my math correctly, and I put 742.9 instead of 742.0. So now I got
Oh, okay.
46. I'm sorry.
No, that's okay. I'm just trusting you guys know what you're doing. So.
Okay. I just
Oh,
wanted
I
to
boy,
need
make
I
it
need to
sure.
was
double
46.
check your calculations. No,
Okay.
46.0. Now that I actually think about it, I actually remember that answer being correct. So very
Oh,
good.
see?
I'm sorry, guys.
I'm,
Oh,
I'm
man.
double
Okay.
checking. I'm double checking. I'm slower than
Ethan,
everybody
where is your
else.
contribution, buddy? Come on, help us out.
I got 46.09.
Oh, okay, well there you go. It's close. That's close enough for government work. All right. So let's take a look at number 2 then. If a gas has a pressure of 12.54 atm and a temperature of 36.8, by how much must the temperature change for the pressure to fall to 27 or 2874 millimeters of mercury. So what are the variables that are in play here?
Pressure and temperature.
Pressure and temperature. And so what variables are not really changing from what we can tell? Because if they're not mentioned, chances are they're probably not changing.
Volume and moles.
Volume and moles. Volume and moles are not factors here, so we can pretty much ignore them, which means that if volume and moles are constant, oh, what the heck did that happen there? There we go. If volume and moles are not changing, then we basically have Gay-Lussac's law, or as I like to refer to it as Ethan's law, for blowing up the compressed air. So then we'll go ahead and list out our elements.
He's a good soldier. He'll take it.
I'm not sure if he's still not on speaking terms with me because of last week, but
Uh-oh, what happened last week?
well, remember I tricked them into and told them they got the wrong answer, and it was like basically all this semantics junk.
Oh,
It wasn't
yes.
that they calculated it wrong.
Yes, yes, that's right. Good memory.
So so what's the initial pressure? What's the P1 here?
12.54
12.54.
ATM.
And what's the initial temperature?
309.95 Kelvin.
Oh, so you mean like the 36.8 degrees Celsius, right?
Yeah.
You already converted it. Nice.
All right. And then you added the 273, because you're right, we have to put it in Kelvin. We have to put it in Kelvin. And if we put it in Kelvin, what did you say that was? 300 what?
309.95.
309.95? You added 0.15, didn't you?
Yeah. My
That's
teacher
what I
tells
thought.
us when there is a decimal, you're supposed to. But when there's not, then you don't have to.
You're actually, technically speaking, you are correct. So very, very well done. I was being lazy. I'm going to admit it. I was being lazy, but that was a good eye. Good call. All right, so now let's take what about the second pressure? Well, there's really only one other, right? 2874.
Yeah, 2874. And it is a mercury.
And do we have any issues with that pressure?
You gotta convert it either way.
Yeah.
Yeah, we got to convert it because it's 2874.
3.78 atmospheres.
All right, so wait, how much? How many atmospheres?
3.78.
3.78 atmospheres. Thank you for that conversion. You could have also converted ATM to millimeters of mercury. It wouldn't have mattered either way, but this is totally fine. And for those of you who aren't sure how many millimeters of mercury are in an ATM, it's 760 millimeters of mercury is equal to 1 ATM. That would probably be given by your professor, but I don't know. It really depends on how nice they want to be.
No, we expect you to remember that. That's basic. One atmosphere. We're going to ask you to memorize this piece of datum.
And then we'll go ahead and we'll use the cross-multiplied form here. So this will be P1 T2 is equal to P2 T1. And I would encourage you to actually solve the algebraic, or like the variable form of this before you plug in numbers. I do think it actually saves a lot of time rather than plugging in the numbers and then manipulating it. So now in this case, I'm looking for T2, so I just have to divide both sides by P1, right?
Yes.
And so it'll be T2 is equal to P2 times T1 over P1. And what do we get? What is our final answer? Let's see if I can get Ethan one more time.
Is it 93.42?
No.
Let's see. Let me check. I'm actually confirming
Yeah, I got
something.
two.
I realize I can't trust you guys anymore.
So I get 93.4
Oh, yeah,
degrees
that's what I got.
Kelvin.
What do you think, Ethan? Is that the right answer?
Yeah, that's what I got.
Cool.
Do you agree? What do you say, sir? Is that the right answer?
I think Ethan may have stepped out.
Oh, okay.
I'm kind of stuck, to be honest. So I'm gonna have to do that one again.
Okay.
Well, shame on me. I will tell you that 93.4 is wrong.
Oh, that's good.
Uh-oh.
And you know why?
Why?
Uh-oh.
Because the question doesn't ask for the final temperature. It says, by how
How much
much
did it
must the
change?
temperature change?
Yeah,
Ah.
Oh.
It's so easy.
Tricky,
Only I could have thought of it.
tricky.
Oh.
So by how much must the temperature change? So in that case,
You got us on that one. Darn.
mhm.
7, 3.
Shame on me. That's why I was trying to get Ethan to give the answer because I was trying to see. Shame on me. I'm being evil. I'm sorry.
Well,
You
you got it
are.
right anyways, so it's
You
okay.
dodged a bullet. You dodged a bullet, Ethan. But you know.
So is
So
it
yeah. So if I take
216.5?
Yes.
yeah, it should be
Yes.
216.5.
Or two.
Okay.
Yes.
Yeah.
Or two. Yes.
Because so basically, if you take the 309, if you take the 309.95
95 or
95, and you subtract the 93.4, you end up with about 216.5. And honestly, the change in Kelvin and the change in Celsius is the same actual change, so it wouldn't matter if you said the change was in Celsius or the change was in Kelvin. It's going to be the same number. But yeah, in this
Question.
case, we did the change in Kelvin. But the only difference in the change in Celsius is that I'd subtract 273 from the top and I'd subtract 273 from the bottom. Well, that would still give you the same difference, right? So now we want to make sure that everybody understands where this all came from. Ethan, what was the issue like that you felt like wasn't making sense here?
I misread the problem. Yeah. I solved for final pressure. I'm sorry, final temperature, and did not find the change in temperature.
Oh, okay. But you did get the 93.4 Kelvin, right?
Oh yeah.
Okay, good, excellent. So I mean, now I will confess that this particular wording, uh, I have seen on some professors' exams. So just do be a little bit careful about it. But yeah, if they really wanted to be jerky, they could put something like this on.
No, it's good. It's good. I mean, it keeps you up on your toes.
Mhm.
that's
All right.
funny.
So the ideal gas law. Okay, so now as I mentioned before, PV over NT P1 V1 over N1 T1 is equal to P2 V2 over N2
That's
T2.
funny.
But it turns out that that's true for pretty much any gas. It ends up being this pretty much this constant, which we call the ideal gas law constant. And so since we have the ideal gas law constants R, we can actually go ahead and rewrite this equation and put it as PV is equal to nRT. So this equation here basically allows us to take, if we have only one set of conditions, so if we have only one set of conditions that we know, we can solve for any other condition, the conditions that we don't know. So for example, if we know the pressure, the volume, and the temperature, we can figure out how many moles of gas we have. And honestly, that's really useful because a lot of times one of the most difficult things to measure in a gas is how many particles you have, how much gas is present, how many grams or how many moles is present. You can easily measure the pressure usually. You can relatively easily measure the volume. And the temperature we have thermometers for, but when it comes to measuring moles, that's a little bit harder, and that's oftentimes what we end up using this particular formula for. So now we come to the end of the gas law, almost the end of the gas laws. We have Dalton's law. So Dalton's law is really interesting. It's basically a very simple law on its face, but actually has some really important applications. So basically what Dalton discovered is that the total pressure in a system of gases, is the sum that sum of the pressures that each gas itself would have if it were by itself in the system. So if I have, in other words, 5 different gases, if that amount of gas were by itself in the container, the pressure that it would have versus the pressure that the second gas would have by itself in the container, and the pressure the third gas would have by itself in the container, and the fourth and the fifth, if I added up all those individual pressures, that would give me the total pressure of the system. So this allows us to speak of gases in a system in terms of their partial pressure. In other words, the pressure that they are exerting, that they're responsible for exerting in the container.
So as you can imagine, the assumption is that there is no attractive or repulsive interaction between these gases, that these gases are just they exert a force on the wall and they have elastic collisions with each other. However,
Yeah.
there's, as Professor DePaul talked about when he initiated the lecture, yes.
Yeah, and pressure basically is the result of collisions of gas particles. And the more gas particles that smack into a particular wall of a container, that's what's going to give you the more pressure. More collisions, more pressure.
Yes,
So,
because by definition, pressure is the force per unit area. So that's the definition. And so based on that definition, then yes, it's absolutely.
And basically, Dalton's law can actually also be expressed like this, although it's usually not. And that's the P1 over N1 is equal to P2 over N2. Basically, the pressure is proportional to the number of moles of gas. So this is, once again, it's another, Dalton's law is embedded in that combined gas law that we talked about before. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. So Dalton's law is in a form represented there. This is the more common way in which you'll see it. But this bottom application is also proportional. And honestly, this can actually be rearranged. If the second pressure is the total pressure, let's say P2 is actually P total, you could actually rearrange this and say, okay, well, I'm going to divide both sides by P total, and this will be P1 over P total. and then I multiply both sides by n1, and that gives you n1 over n total. So this is interesting because basically what this means is that the pressure fraction is equal to the mole fraction. So if a gas occupies or provides half the pressure, it's also going to provide half the moles. So these three equations are all in effect implications of Dalton's law. That's kind of cool. All right. So basically, if you have 0.6 moles of H2 and it has 2.9 ATM, and 1.5 moles of HE that has 7.2 ATM, if I combine those moles, see I also and moles of gas into the same container, I end up getting 10.1 ATM. And notice that the volume and the temperature stays the same. And if you did the P1 over V1 is equal to P2 over P1 over N1 is equal to P2 over N2, you'd find that it actually does have that same valid proportion there.
Yes.
Cool. So, any questions on this before we go on? Does this make sense?
I'm good with it.
Okay, cool.
Yes.
So now we're going to deal with the thorny issue of vapor pressure. So water evaporates, and pretty much most other liquids also evaporate to some degree. And as a result, when those particles evaporate, they turn into a gas, they slam into the sides of the container, and they create a pressure. Now, water only reaches a certain pressure. So like, for example, if I have a container and it's sealed on the top, let me change my color. I'm going to make it blue like water. Okay, so let's say I have some water in here, okay? If this initially so at different temperatures, water will have a certain amount of gas particles that evaporate. And you'll see a little particle evaporate here and a little particle evaporate there, shooting out. The highest energy particles, highest energy water molecules will evaporate, and it will evaporate until there's a certain number of particles above the surface of the liquid. But once it reaches a certain saturation point, what happens is that there's so many particles of water above that the number whenever a gas particle of water molecule hits the surface of the water, it has a chance of being sucked back into the liquid phase, pulled back in. So eventually what happens is that once it reaches equilibrium and you have a certain amount of gas particles in the air, and they're all flying around or whatever, the number of particles that are leaving is roughly equal to the number of particles that are going back into the liquid phase. So it starts out with a bunch of particles leaving the liquid phase, and eventually you get to the point where the particles leaving and the particles entering they're doing so at the same rate, and this is what's referred to as dynamic equilibrium. So it's a dynamic equilibrium. And actually, I'm going to go ahead and write that down.
Yeah, so you've described it very well pictorially. So one thing that we have to emphasize here is that vapor pressure is defined for closed systems. So if you could write here, if let's see, can I write here? No. So a very important concept is that the system has to be closed.
Very, very important point. Thank you, Dr. Neal. You're absolutely right. It's the system. In order to have a vapor pressure per se, the system must be closed.
Yes.
Now, that's not to say that the vapor wouldn't have any pressure. It wouldn't really be measurable or consistent because it will continue to evaporate. In an open system, it'll just continue to evaporate and become part of the air. But in a closed system, it'll reach dynamic equilibrium, and then you'll get this phenomenon of vapor pressure, where at a particular temperature, it always has the same pressure.
That's right. So at equilibrium, the rate of the water particles going into gas phase is equal to the rate of the gas particles going back down to the liquid phase.
And so why is this important? Well, this is the reason why this is important, and you'll actually do some labs like this. Hopefully, if you guys take chemistry 2 in the fall, I don't know if you're taking it over the summer in the fall, but if you take it over the fall, you'll actually be doing labs in classrooms again. And you will be collecting some gases over water. And the thing is, when we collect gases, we oftentimes collect them over water to make sure that we collect all of the gas and it's not mixed with the gas from the air. It's not mixed with the air. And so since gases are collected over water, these are closed systems because it's sealed essentially in a glass container where there was only water present, but now there's gas. And so it's a closed system. And therefore, we have to take into account the vapor pressure to figure out how much gas was collected. And so this vapor pressure of water has to be, like it says here, subtracted from the total pressure. Otherwise, we'll assume that we have more molecules of gas present than we actually do, or more molecules of gas produced than we actually did.
Yeah, in other words, this is another application of the Dalton law, because remember that the total pressure is the summation of the partial pressure of the individual gases. So yeah, there you go. Thank you.
Mm-hmm. Any questions about this?
It's a very beautiful concept.
Cool. All right, now we just have one last gas law. Oh no, you have two gas laws. I lied. You have Thomas Graham, and he doesn't look like a terribly happy fellow. Not necessarily somebody you'd want to bring to a party. But yeah, basically, Graham came up with this law of fusion, which basically states that he noticed that there's this pattern of a fusion. Now, a fusion is when essentially a gas escapes from a narrow hole in a container. So if you have a container here and you put a tiny little hole in it, the rate of escape of the gas, the rate at which the gas escapes, is called its rate of effusion. So the rate of effusion of a gas he determined is inversely proportional to the square root of the mass of its gas particles. So inversely proportional to the square root of its mass. So you may have noticed that if you've ever gotten a helium balloon, that a helium balloon will shrink in size more quickly than a balloon filled up with ordinary air. And the reason is because a helium balloon, the molar mass of helium is only about 4, whereas the average molar mass of the gas particles in a blown up balloon is, it's a mixture of nitrogen and oxygen and carbon dioxide. More carbon dioxide if you blow it up yourself, and that means that you end up having average molar mass in the early to mid 30s. So if you compare molar mass of 4 to molar mass of 30, the rate of effusion is going to be a lot faster with helium. So,
Yes.
so the rate of effusion of a gas is proportional to 1 over the molar mass. And if you divide this expression by another expression, basically rate 1 over rate 2 is equal to 1 over the square root of that. That essentially, you get this new equation here, which is very useful for relating how much faster one gas will effuse versus another. And this m is not molarity here. This is actually molar mass, the molar mass of gas 1 and gas 2. So rate 1 over rate 2 is equal to the square root of molar mass of 2 over the molar mass of 1. Notice they're on opposite ends. They're on opposite ends. The 1s and the 2s are on opposite ends of the fractions because it's an inverse relationship.
And this is something you have to pay attention to because under the duress of a test, a lot of students, they reverse the ratios. They're doing problems quickly and they go, oh, that's rate 1 over rate 2 is equal to the square root of m1 over m2. So yes, do note the inverse proportionality.
Mm-hmm. And diffusion is a little bit more complex, but it does follow the same principle that when gases diffuse, when gases move out, that heavier molar mass gases are going to move out more slowly. So this is important in cases like, let's say, if there's a gas explosion and there's toxic gases that are spilling out of a factory or something like that. We want to actually know how fast these gases are traveling and if they're going to hit a city or if they're going to hit certain wildlife areas and things like that. So in cases of emergencies, this type of information is actually crucial.
Yes.
So yeah, because and with the balloons, there's a little tiny holes in the pores or in the rubber of the balloon, and the gases escape through those pores. So that effusion occurs here, and you can actually see the result. After 48 hours, the helium balloon is noticeably smaller. Now let's do some practice. Yay, practice! Okay. So the first thing we want to do is we want to identify what type of law we might be dealing with here. So in the case of the second set of problems, so the 5.42 container is holding a gas at 789 millimeters of mercury and 23.83 Celsius. If the mass inside the container is 0.214 grams, what is the molar mass of the gas? So there's three different types of new gas laws that we picked up on, right? There was Dalton's law. There was Graham's law. Of effusion. And then there's the ideal gas law. Now, Graham's law always deals with the effusion or the rate of movement of a gas out of a container. Does this number one problem look like it might be appropriate to use Graham's law for? What do you think?
No.
No. And we don't really have any gas moving in or out. And then since the truth is that Dalton's law is really kind of part and parcel with the combined gas law. So I'm actually going to draw the combined gas law with Dalton's law, even though they're not exactly always the same. I'm going to go ahead and include this. Because the two, I will tell you this, 95+% of the time, the laws that you're going to use is either going to be some derivation of the combined gas law, or it's going to be the ideal gas law.
You mean some
And how do you know which
variation?
one to use? How do you know when to use P1, V1, T1 is equal to P2, V2 over N2, T2? And how do you know when to use the ideal gas law, PV is equal to nRT? It comes down to the number of sets of conditions you have. Do you have one set of conditions? You have one set of conditions, you use the ideal gas law. If you have two sets of conditions, you use the combined gas law. In other words, do you have two temperatures, two pressures, two volumes? Or do you only have one temperature, one pressure, one volume? So basically, looking at those two, which would I use? Would I use the combined gas law, Dalton's law, or the ideal gas law for problem number 1?
Ideal.
Would you say?
I'm sorry, which one?
Said ideal.
Yes.
Yeah, you'd use the ideal. Now, even though technically speaking, the molar mass is not in the ideal gas law in this form, keep in mind what the molar mass is. The molar mass is simply, molar mass, a fancy cursive M is sometimes used for molar mass, but molar mass is equal to the grams divided by the moles. Well, I have the grams, which means the only thing I need to solve for molar mass is the moles. And I can solve for moles with the ideal gas law. I'm going to use the PV is equal to nRT. And let's list out our variables. What's the pressure?
789 millimeters of mercury.
Yeah, 789
Yes.
millimeters of mercury. And what's the volume?
5.42 liters.
Very good, 5.42 liters.
Yes.
And the number of moles, well, that's what I'm looking for, right?
Mhm.
And then there's the R value, the ideal gas law constant. And I'll get to that in a second, but we also have a temperature of 23.8, which we have to convert to
Kelvin.
Kelvin. So if I add 273.15, since Elena's going to yell at me if I don't use 273.15, I got to use the 0.15.
Thank you.
No problem. And so that's going to give me 276, or
No.
296 rather.
Yes, 297.
296.95, or
Oh.
yeah, it would round to 296.70 with appropriate sig figs because I have to round this. Not too often I get to use the rule of perfect fives. See, Dr. Neely laughs because she's the only one other than myself who's nerdy enough to know what the heck the rule of perfect fives is. So R value, okay, so the R value, the constant, the one we use most commonly is 0.08206 liter ATM, liter times ATM per Kelvin mole. While there are other versions of the of the ideal gas law or the ideal gas constant you could use. Like technically speaking, I
Now,
could, if I
for me,
wanted to,
for
use 62.4 millimeters of mercury. I could use 62.4 millimeters of mercury, 8 liters per Kelvin mole. Essentially, the number for the ideal gas law constant is dependent upon the unit of pressure that you use. Another common one, a common one that's also used for the ideal gas law constant is you could also use 8.314 kPa, kilopascal liter per Kelvin mole. But to be honest with you, you don't
99,
necessarily want to have to
right,
memorize like 3 or 4
right,
different
right,
ideal gas law constants. It probably
right.
would just be easier to convert the pressure to ATM.
Yes.
If you were going to keep the pressure in millimeters of mercury, you would have to use this guy. But we're not going to actually use these guys. I'm going to actually go ahead and erase them just so I don't confuse you. Okay. Hope you enjoyed that theme music. And then, so then we're going to go ahead and convert. Oh, where's my little inky thing? Ah, okay. Here we go. We're going to convert 760 millimeters of mercury is equal to 1 ATM.
8,
1
9
ATM.
divided by 7,
So I have
60.
just a real quick question. So we're converting millimeters of mercury to atmospheres because we're using the ideal gas law?
Because we're using the ideal gas constant. Essentially,
With the R, right?
yeah, the pressure
Okay.
unit that you use the pressure unit in the ideal gas constant has to match the pressure unit you have here. That's why I said if I wanted to leave it as 789 millimeters of mercury, I could, but then I would have to use 62.4 millimeters of mercury liter per Kelvin mole for the R value.
Okay, got it. Okay.
Yeah, essentially, whatever the pressure unit is for R, I have to use that same unit. I have to use that same unit for the pressure. In this case, since the most commonly used one and the most commonly given one by professors will oftentimes give this constant to you. Not always, but sometimes, usually. Um, but they'll usually only get, oh my goodness, what did I do? They'll usually only give you, they'll usually only give you one. They'll usually only give you one, and it's usually this one, liter ATM per Kelvin mole. Okay, so now all we have to do is plug in our, well, first of all, we calculate our pressure. And what is our pressure?
1.038 ATM.
We can just say 1.04 because 3 digits.
Okay.
Now, technically speaking, it's good to actually hold on to significant figures until the very end of the problem. That's
Darn
totally
good
fine to
point.
keep a few extra sig figs, but do make note of how many sig figs you have. What did you say it was? 1.038?
38. Good job, Koti or Anna.
Okay, so 1.038, we'll keep that there, and we'll just note that that's 3 significant figures, and pardon my like sloppy writing. And now we have PV is equal to nRT. PV is equal to nRT. And we can solve for n just by dividing both sides by RT. I miss Ethan. He hasn't been talking much this session.
He's being pensive. Ethan is having a pensive session.
He's a thoughtful guy, I understand. All right, so the pressure is 1.038 ATM
I think Ethan may also have a weak connection because whenever he wants to talk, the energy level of the indicator is very low. So maybe that's another reason.
Oh, that could be. Pressure times volume, so 5.42 meters. And then our value is 0.08206 liter ATM over Kelvin moles. And then times temperature, which is, I don't know, something, 297.0. There we go. That's Kelvin. And one of the cool things you'll notice here is if you write all your units, units can really be a guide as to whether or not you've actually done the problem correctly. Because if you pay attention to your units, and they should always cancel out to give you the unit that you want. So this is, I have liters, cancel out here. I have ATM, cancel out here. I have Kelvin, cancel out here. And I'm left with moles. And moles is, it's actually 1 over moles. So that flips it to moles. Well, moles is in fact what I'm looking for. That's what N is. And so that's good. That's actually, I'm getting what I want to get. I'm getting what I should be getting. So go ahead and calculate that for me and tell me what you get. Type it into the chat, all that kind of stuff.
0.231 moles.
Yes. Yes.
Is it 0.231?
Yes.
What? That doesn't sound right. I don't believe it.
Huh. That's what I got. I can redo it. Let's see.
No, I believe the number. I just I realized I probably should have designed this problem a little bit better so that I was ending up with a molar mass that's, I don't know, greater than the mass of a proton. So,
Oh, yes, yes.
yeah, because so if
214
if
divided
you
by
were a scientist and you got this result, you would have to seriously question your laboratory method because there's no that, or you would be like, oh my gosh, look what I discovered. But probably more likely, this is like, oh yeah, I think I made a mistake somewhere. It's like the time I created antimatter. I measured, so I just divided grams per moles. No, I actually, in organic chemistry, I measured, or I made this product, and then I zeroed out the scale. I put the watch glass on it and I zeroed it out. And then I scraped my tiny little bit of product onto the watch glass. And instead of giving me a positive mass, it gave me a negative mass. And I was like, oh, look, I created antimatter.
Antimatter, there you go.
So somehow I feel that there might have just been an error in the scale because
Obviously.
otherwise, yes. Otherwise, I should be making millions right now because I just created antimatter.
Right. Without using
paper.
you created antimatter without the use of $1 million machine, the linear accelerators or the cyclotrons, which are actually beyond millions of dollars.
Exactly. Yeah. I'm the next Elon Musk.
There you go. Oh, you're very welcome, Koti. Yeah, Professor Deplan, I'd like to have fun with science.
So 0.926 grams per mole. All right, so that would be your molar mass. A questionable molar mass, to be sure, but that would be our molar mass. By the way, if you were trying to figure out the molar mass of a gas, what is likely the smallest molar mass of a gas you could ever come up with?
32. Wait,
No,
maybe
not
that
quite. That
doesn't
would
make
be
sense.
so there are gases that are lighter than that, right?
Right, but we were looking for the large one, weren't we?
No, I said what would be the smallest molar mass that you could get?
Why
It
would
would
it
probably
also
be
be 2.02?
It would be 2.02.
Yes.
That would be the smallest
Yes.
molar mass you could get, because it would be the molar mass of
Yes.
hydrogen. I thought you said 32. I might have been wrong. But yeah,
I think-
No, I said both.
Diatomic.
oh,
Yes.
okay, yeah. 2.02 is absolutely correct. Yeah, because hydrogen is diatomic. It doesn't exist by itself. So if you get a molar mass
Yes.
of a gas of less than 2.02, you probably made a mistake somewhere. So unless you're working on a problem like mine, which makes no sense. Now, number 2, it says, what is the pressure exerted by 2.5 moles of gas that occupies 10.45 liters at a temperature of 21.5 degrees Celsius? What type of gas law would I use for this one?
Pevner. Sorry, ideal gas.
Yes.
Huebner, yep, ideal gas law, absolutely. That's exactly what you'd use. Now, since this is very similar to the previous one, only a little bit easier, I'm actually just going to go ahead and skip this one because I think you already know how to use it. And I want to get to some other things before we run out of time. Number 3 says, what is the temperature at which nitrogen gas would have a density of 2.51 grams per liter at standard pressure? Okay. What type of gas law would I use for this?
I think you could use ideal gas.
Yeah, you would
Yes.
use the ideal gas law. Now, there's actually a couple of different ways to do this if you use the ideal gas law. So PV is equal to nRT. So it says standard pressure. Now, if ever it says standard pressure, you know that means 1 atm. And standard temperature STP, this is a reference, standard temperature and pressure. Standard temperature is 0 degrees Celsius, and standard pressure is 1 atm. All right. So in this case, what is the temperature? Now, here's the thing. There's a couple different ways to do this. To use this formula as is, you can assume 1 liter. Because if you assume 1 liter, how many grams do you have?
2.51.
Yeah. That's 1 atm for your pressure, the volume. And when it says standard pressure, we're going to assume exactly 1 atm. So there's unlimited sig figs there. And I'm assuming 1 liter of volume. Once again, I'm assuming exactly 1 liter. So unlimited sig figs. Then I have nRT. The temperature is what I'm looking for. The R value is what we all know what it is. Now for the number of moles of gas, because I assumed 1 liter, that means I have 2.51 grams of nitrogen gas, which of course is N2. And then I can just go ahead and use the molar mass of N2, which is 28.02. And then I can convert that to 1 mole of N2. And so if I do that, then I can solve for what the temperature would be based on that. Now the other option here is to actually solve for the density itself. And it turns out that moles is just the grams divided by the molar mass, right? So I can actually rewrite this equation as PV is equal to the mass divided by the molar mass, MRT. And that gives me PV times the molar mass is equal to the mass of the gas times RT. Now the cool thing is here, if I wanted to, I could go ahead and I could solve for the molar mass directly here with a particular thing. The other thing that I could do is I can divide both sides. Michael. Yeah, hold on. I can divide both sides by the volume here. And mass divided by volume is density, right? So I can actually solve for pressure times the molar mass is equal to the density times RT. And the cool thing about this equation is that it doesn't require me to make all sorts of different assumptions. So but of course, I mean, if you had this memorized, yeah, using this would be a little bit easier. But if you just had the PV is equal to nRT memorized, you could use this. You could just use that one. Does that make sense?
Barely.
Yes.
So these are just a couple of different versions of the ideal gas law equation that can be helpful. So I'm going to skip number 4. Well, actually, we're going to actually have to. We've run out of a little run out of time. Number 6 is going to be Graham's law of effusion, of course, because it talks about the effusion of a gas. It effuses. And then gas collected over water, number 5. Dalton's law of partial pressure is going to be appropriate here. And the number 5 is actually tricky because it's going to be a combination of the it's going to be a combination of the combined gas law and Dalton's law of partial pressure. Shoot, I wish I had more time to go over this. I'm running out of time. I don't know if I can really cover much more effectively at this time.
Thanks everyone for coming tonight, and we shall see you next Monday evening. Good night.
Yeah.
All right. Thanks
sorry,
a bunch,
Thank you.
guys.
We're sorry I wasn't able to get through more. If anybody has any questions over the rest of this, please feel free to contact me. I do have the complete answer key, I think, posted on the website. The complete answer key for all of those, including the ones that we didn't get to work through. Let me double check and make sure that that is true. Yeah, okay, so the complete answer key is posted on the website with all the work shown. So that'll have the answer key for all of the different parts. And hopefully that'll answer all your questions. Also, feel free to look at the latter part of the where it talks about the difference between real gases and ideal gases. This is something you will be expected to know. It's not so much in terms of, you won't be expected so much to know this in terms of calculations wise, but you will be expected to know the principle of when do gases no longer behave like ideal gases? What's the difference between real gases and ideal gases? And so you'll get to learn about this handsome gentleman, van der Waals. He's one of the, he's probably the best looking guy on the, not that I look at guys or anything, but for the chemist on the gas laws. So. All right, cool. Well, y'all have a wonderful evening, and thank you for coming, and we'll see you next week.
Have a great week,
Thank
Professor.
you.